Hello, everybody. Today we are talking about algebraic proofs. This is lesson 2.6. We'll have another lesson with slightly more complicated algebraic proofs or slightly more complicated examples. But for today, we're just introducing the topic. That does mean today you're going to be doing technically your first proofs. But my hope is that we'll see this is actually much more familiar of a topic than you might be expecting. We're going to use the word here as a way of getting started. So if you're watching this video, my suggestion is to go ahead and pause for a moment and work on this warm-up where you are solving the given formula for the variable p. So I'm going to go ahead and work through our problem on the count of 3. So if you need to pause, go for it. 3, 2, 1. Let's jump into this. All right, so we're starting off with this equation, 2m equals 3np over 4. All right, so if we're solving the formula for p, that means essentially we want p by itself. So I'm just going to sort of translate this. Isolate is the phrase we might use. Isolate p in this given equation. Right now, none of the variables are isolated. We want p equals or something something equals p. So let's see, what might we need to do first? I'm going to focus on what's happening to p right now on that right-hand side of the equation. And something that's happening to it is it's being divided by 4. That whole side is being divided by 4. So if I'm going to get that p by itself, I need to be using all my inverse operations. I need to undo what's happening to p. So I might start by multiplying both sides of my equation by 4. What that effectively does is cancels out our denominator. We get 8m equals 3np on the other side of our equation. Okay, so still we have some things happening to p. 3 is being multiplied by p, n is being multiplied by p. So we need to undo those things. We can undo them at the same time. Now undo, inverse operation of multiplication, would be division. So I'm going to divide both sides by 3n. So that cancels out our 3, cancels out our n, and we're left with on that left-hand side 8m over 3n equals p. And thus we have isolated our variable p. It's all by itself. So this is the solution to this formula. Okay, so let's take a look at our algebraic proof. So first, what we're aiming to do, we're going to be applying properties of equality to justify provided statements, given statements, and use properties of equality to write 2-column algebraic proofs. Okay, so some vocab all associated with proofs. Let's start with our properties of equality. Okay, so you have this list presented to you. Now, when I say we're going to need to memorize this list, it might immediately look a little bit intimidating, which is totally fair. But what we're looking at is stuff you already know about. This is something that is certainly talked about in Algebra 2 and Algebra 1. And the first 4, in fact, are things we do all the time when we are solving equations. So let's look at first our addition property of equality. What this says is if we have some equation, we're starting in some really generic spot with just a equals b. Then a plus c equals b plus c. So what's different there is, well, we've added c to both sides of the equation. So the addition property of equality is essentially just stating that we're allowed to add something to both sides of the equation, and it maintains equality. Each side is still equal to the other side. We do that a lot. We use our subtraction property as well. So notice that in the subtraction property of equality, we're saying we're allowed to subtract C, to subtract something from both sides of the equation, and it's still going to be true. Likewise, we can multiply both sides of our equation by something, and it will still be true. And of course, lastly, we can divide both sides of our equation by something, and it will still be true. So we're going to be memorizing these, using these as essentially reasons we're allowed to do things to different equations. And we're going to want some sort of way to perhaps abbreviate these names, because like writing out the addition property of equality every time we're wanting to provide this as justification, it's going to get a lot, like a lot of writing. So here's why, or here's how I should say, we tend to abbreviate. So the addition property of equality, I might label that the add POE. Subtraction property of equality, similar. I'm actually going to do sub R, or I guess I should really do sub T, shouldn't I? Why did I do sub R? Sub T, POE. Now, POE here in both cases is standing for property of equality. Multiplication, we're going to do perhaps just mult, POE. I guess you could do just MUL if you prefer. And division, we're going to call that the div POE, division property of equality. So later on when we talk about actually using these properties and perhaps providing the names as our justification, we can use these abbreviations for sure. Okay, so those are the first four, all really similar to each other. The next ones, again, you're definitely going to find these are somewhat familiar. Shouldn't be the first time in the world you're ever hearing about them. We have the reflexive property, reflexive. Now, the reflexive property of equality seems really simple and perhaps odd that we would even bother. Now, it seems that way, but I guarantee you we will, in fact, use this a lot. What the reflexive property says is that something is equal to itself. A equals A, 0 equals 0, X equals X. It could be anything equals itself, and we will indeed use this frequently. Maybe just a tiny bit today, but as the year goes on, we'll end up using this quite a bit. And we'll talk later about why it's really helpful. For now, just know that when we are saying something is itself, we're using the reflexive property. Next, we have the symmetric property of equality, which is kind of saying if we have some equation, again, real simple, A equals B, then we can flip it around. In other words, we can mirror it. So the reflection, now notice reflection in a mirror is backwards, right? The reason we get these two mixed up is because we often think about reflection versus reflexive. So here's something I like to call out about our reflex property, just to go back to that for a second. I like to kind of say to myself, like, it's a reflex. It's so obvious that it's a reflex to say this. Whereas the symmetric property, this is where we're really like mirroring the equation. We're flipping the equation around. It's a mirror of itself. Maybe it's not super helpful to use the word reflection just because we want to avoid that confusion. But the symmetric property is mirroring our equation. Now these, again, do get abbreviations. Reflexive property, I tend to just do reflex POE, reflex POE. And for the symmetric property, kind of similar, I tend to do SYM POE. I guess you could add two M's if you wanted, but whichever is okay. It gets the point across. Next up, we have our transitive property. This is something we'll use a lot of as well. The transitive property of equality states if we have two equations, A equals B and B equals C. We kind of talked about this transitive property when we mentioned the law of syllogism as a reminder. So notice one side of my equation matches the other side of the other equation. That's kind of our, so to speak, middleman that we get to cut out. The transitive property, I'm really stuck on reflexive, the transitive property of equality states, if A equals B and B also equals C, then A equals C. So we cut out B entirely, we cut out the repeated element of our equation to conclude A equals C. And I will often abbreviate this trans, you could say POE. Okay, moving along, we have our substitution property of equality. Now, the substitution property of equality is something else we do a lot of in algebra contexts. So we're kind of saying we have some information that A is equal to B. I'm not going to refer to it as an equation right now, but let's say we know A is equal to some number. A is 5. We solved for A and found out it was 5. Well, then we can replace the variable A with the number 5 in our equation. We can substitute whatever we just found for our variable in for that variable in the equation. Now that's true when there's no actual numbers involved as well. Like here it's just saying if A is B, then A and B are interchangeable in an equation or an expression. So that is our substitution property of equality. Now this one I tend to just call SUB-POE. So notice the slight difference here in the substitution property and the subtraction property abbreviation. We could be a little bit more clear perhaps and call this SUBS, substitution property versus subtraction property. But again, we just want to make sure we're being clear enough that we know what we mean. The last one here is our distributive property, which again, we can abbreviate like this, dist-P. It's not actually a property of equality, so we might just do prop, dist-prop. And the distributive property tells us that these two sides of our equation are equal. If we've got A times the sum of B plus C, then A times B plus A times C is the same thing. In other words, we can, in fact, distribute A across the parentheses. All right, so those are our properties of equality. Again, not totally new and probably feeling very algebra right now, but hey, we are talking about algebraic proofs. So we're going to go ahead and you can certainly refer to your list of those properties of equalities for now. Just know that you are going to be expected to know those, to be able to use those on a quiz without having a list to reference. So here's some examples to get us started. I want you to take a look at each statement and provide the property of equality that justifies why these things are true. So again, pause the video to give yourself some time to practice. And I, at this time, am going to go ahead and write down our answers. So if you need to pause, still do so. For number 1, the measure of angle A equals the measure of angle A. This is our reflexive property of equality. In number 2, if BC equals CD, notice that's saying the measure of segment BC is equal to the measure of segment CD. So we know that, and CD equals EF, then BC equals EF. We're cutting out our middleman, so to speak here. This is our transitive property of equality. Okay. Next, if x equals 3, then 3 equals x. That's our mirror, right? That's the mirror image of each other, those two equations. So this is our symmetric property of equality. Lastly, if x equals 3 and y equals 3x plus 5, then y equals 3 times 3 plus 5. That would be our substitution property of equality. All right. So moving right along here, let's talk about what is a proof. So a two-column proof is another term for a formal proof, and it's always going to contain statements and reasons. Reasons are the same thing as justification, organized into two columns. Okay, and I might just write like in parentheses, justification next to reasons. Ooh, justification. All right. I would also maybe add here that our statements and our reasons, we're generally going to number them just so we can see like which statement lines up with which piece of justification, with which reason. So you always have like one statement corresponding to number one reason. Now we're going to give this a little bit of practice. So here is our first proof. Woohoo, here we go. We want to write a two-column proof to verify the following conjecture. Okay, so remember, what is a conjecture? It's an if-then sort of statement. So if the distance d an object travels is d equals 20t plus 5, then time t is t equals d minus 5 over 20. So basically, this is like what we did in our warm-up. What we want to prove is that t equals d minus 5 over 20 if the information we're starting with is that d equals 20t plus 5. In other words, in this particular proof, we're literally just going to be taking what we're starting with and getting to what we're ending with, and with each step, providing a reason, providing some kind of property of equality. So let's go ahead and start. I'm going to go ahead and write my first statement, number one. We're going to start just with that original equation, d equals 20t plus 5. And for my justification there, well, how do I know that? Well, it was in the problem to begin with. It's what I was starting with. In other words, it's what I was given. You will always have your first line of a proof be, this was given information. You might even have multiple lines of given information. So that's our given. That's our equation we're starting with. Okay, so let's see. What do we need to do next to get t by itself? Now, I might show my work like in a different color. Generally in a proof, you don't necessarily show your work, but I'm just going to show what's happening from line to line. In this equation, I might start by subtracting 5 from both sides. So my next line, I'm going to write this back in my like normal, this is my proof color. My next line might look like d minus 5 equals 20t. Now, how do I know this is true? Well, let's think back to what we did to get here, right? We subtracted 5 from both sides of the equation. So really what we've done is we've used the subtraction property of equality. Okay, so this should feel like, oh, we're just like being extra careful to state why we're allowed to do what we're doing to our equation. That's exactly what's happening. Next thing I might do is, let's see, divide both sides by 20 if I'm trying to get t by itself. Okay, so the next line, the result of doing that work is going to be d minus 5 over 20 equals t. And what we did was divide, so we used our division property of equality. Okay, so you might think, all right, we're done, ta-da, but we're not quite. This, unfortunately, is the first opportunity I have to talk about how picky, granular, whatever word you want to use, we tend to be when we are proving. So take a look at what we were asked to prove, the conclusion part of our sentence there, versus what we have in our proof at the moment, that line number 3. It's almost the same, but it's backwards. We need to flip it around. We need it to be exactly what we aimed in the beginning to prove. So we are allowed to flip it around. We're all allowed to say, oh, so t equals d minus 5 over 20. That is precisely what I aim to prove. And think to yourself for a second, what is it that allows me to flip the equation around like that? Or give myself a mirror image, perhaps? That would be my symmetric property of equality. And congratulations, you've just done your first proof. Okay, that is an algebraic proof, in fact, that we just did. And I want us to take a moment to define this. Later, we'll be doing two-column proofs that are not just equations, but this is how we're starting. Take a look here. So an algebraic proof, that's what we literally just did here. An algebraic proof is going to be any proof that's just made up of a series of algebraic statements. And that's what we're going to get more practice with here. Okay, so let's go ahead and look at our next example. We are going to write an algebraic proof, okay, to solve the following equation. Now, we're just solving the equation here. We don't necessarily have a specific value we're trying to prove A is equal to. Our proof is going to be over once we have solved for A. So sometimes algebraic proofs will be in that sort of format. All right, so as always, we'll start our first line with the given information or the given equation. 5 minus 3a minus 4a plus 7 equals 92. That is our given information. Now, it's always important to write down your given information because honestly, when I'm grading proofs on tests and quizzes, that's always worth a point. That's always something you can add to your proof. Okay, so what would we do if you would like to challenge yourself to do this now that we know what an algebraic proof generally looks like? Go ahead and pause. Otherwise, we're going to go ahead and walk through. I might still show my sort of work in a separate color. So notice what I'm doing is distributing. In other words, I can even write immediately that I'm using the distributive property. Okay, so what is my result of using the distributive property? We have, let's see, 10 minus 6a minus 4a. Notice we're distributing the negative 4 minus 28 all equals 92. Okay, now my next line, what would I do next? I might combine my like terms. Let's see, switch that to white. Combine my like terms. So if we do that, our next line might look like total of negative 10a minus 18 equals 92. Now, combining like terms isn't exactly a property of equality. So here's what we tend to write as our justification. Well, one is combine like terms. That's simple. This is what I suggest. I see sometimes people put simplify instead, but I think sometimes that can feel like too big of a box. So my recommendation is to put combine like terms. Okay, next thing we might do is actually add 18 to both sides. So our next actual line would look like negative 10a is equal to 110. So we have added to both sides. We've used the addition property of equality. And last thing we would do is divide by negative 10. In other words, I'll fill in the reason here first. Use the division property of equality. So our last step is actually writing, well, okay, A equals, and what do we get there? Negative 11. Okay, so far the algebraic proofs we've written have basically just been solving an equation or manipulating an equation and providing written justification for each step. Okay, Let's do maybe a couple more examples. I'm going to leave some of the examples that you have in your notes like to you as practice, so that this video isn't like, too long. Let's jump into, yeah, this one's a good one, I think. We have the area of a trapezoid is equal to A equals 1/2 times base 1 or B1 plus B2 times H. So the height h of the trapezoid is h equals 2a over b1 plus b2. Okay, really similar again back to our warm-up where we are manipulating the original equation. Maybe I'll write like this is our given. And we want it to match up in the end to this equation. So I'm going to write that's what we're trying to prove. So honestly, you could go ahead and write all of your statements first, like number each line, and then fill in your reasons. Maybe we'll do that in this example just to show that that's possible. It's not going to necessarily be so possible when we switch to doing not like strictly algebraic proofs, but for now, you could totally do that. So I'm going to rewrite A equals 1/2 times B1 plus B2 times H. And as my next line, let's see, what do we want to do? I guess there's a variety of things we could do. Something I'm inclined to do is like cancel out that fraction first. So maybe I would multiply both sides by 2. I'm going to write that as 2 over 1 on the other side, on the right side that is. So we're going to be left with, as our next line, 2a equals, and now we just have b1 plus b2 times h. Okay, so again, I'm trying to get h by itself. Right now it's being multiplied by b1 plus b2. We can, in fact, divide by b1 plus b2. I'm going to keep that in parentheses for now. Got to do that on both sides. All right, so the next line would look like 2a over b1 plus b2 equals h. We have the same issue as we did last time, or perhaps the first time, which is that we've got the meat of it, but it's in the wrong order. So last step is going to be, I think I labeled that previous step as 2. Let's fix that to 3. Our last step 4 is going to be to reorder that. H equals 2 times the area over base 1 plus base 2, b1 plus b2. Okay, let's fill in the reasons. Take a moment and try to test yourself. Pause the video. Number ones are given for 2. Again, we're writing the justification from going from step 1 to step 2. So what did we do to get there, basically? And we multiplied by 2 on both sides. So we used the multiplication, let's make that a little more clear, multiplication property of equality. From 2 to 3, we divided both sides by the same thing. So we used the division property of equality. And for step 4, we literally just switched the order. Now that's not the reflexive property. Reflexive property would be to say like h equals h, which we did not say here. So rather, this is our symmetric property of equality. Okay, another proof down. Okay, let's see, do I want to do this one? I think I'd like to look at one more, and not this one, because I think this one is going to be just slightly more complicated. Okay, so there's a little bit more going on, but really this is going to be an algebraic proof. There's just a little bit of like geometry going on here as well. So we are given that angle JGF, okay, angle JGF is congruent to angle JGK. So I might mark that immediately on my little given diagram. Okay, so those are my JGF and JGK. And then I'm also given that angle JGK is congruent to angle KGH, which is the other one there. Okay, so I'll mark that one as congruent as well. Now, the information in the diagram is also included as information that's given. So not only the information that's in this sentence here about the congruent angles, but also the fact about 6x plus 7 and 8x minus 5 is being given angle measures. Okay, so I'm going to go ahead and rewrite my given statement. We have a lot going on here. We're going to write that angle JGF is congruent, angle JGK. Angle JGK is congruent to angle KGH. And I'm also going to go ahead and throw in that the measure of angle JGF, had to remember which one is that. That one is 3x plus 7, and the measure of angle KGH is equal to 8x minus 5. So before I begin, oh, and I'm also trying to prove, I'm not sure if I read that last time, x is equal to 6 is what we're ultimately trying to prove. Okay, so I might draw my 2-column proof on the remaining area of the screen here, but before we do that, I'm just going to kind of talk through like what we're aiming to do here. Notice that we've got 2 congruent angles and then 2 other congruent angles, but this angle JGK shows up in both of them. So I'm thinking that serves as kind of like a middleman, like I want to cut that out, right? And I want to say, well, the measure of angle JGF has to be congruent to KGH. That's really where I want to get, because those are the 2 angle measures that I'm given to work with. Now, in order to use that, well, right now we've got properties of equality, but not properties of congruence. Maybe later we'll talk about things called properties of congruence, but we don't have those right now. So I'm going to need to kind of convert these congruence statements, so to speak, into equations instead. And that means basically rewriting, let's take this for example, rewriting that congruent statement to say, well, if they're congruent angles, then we also know that their measures are equal. The measure of angle JGF is equal to the measure of angle JGK. And we could write the same sort of thing for the other congruence statement. Now, how do I know that? How do I know the measures are equal just because they're congruent angles? Well, that is going to be the definition of congruence. That is, in fact, another fact we can use in our proof. So we're going to try to put that together. Eventually, this is going to turn into a purely algebraic proof. But for now, we're going to do a little bit of definition of congruence stuff. Okay, let's make our table here. So I'm going to try to draw a straightish line, another straightish line. Okay, so we've got over here our statements. Maybe I'll switch from white so it stands out a little bit more. Okay, so if you don't have a table already drawn in your notes, then you want to be drawing your own here. Okay, so here's how I'm going to list my my given information, because there's a lot of it. I'm going to sort of list it out, like here's step 1, and here's the first part of step 1, like A. Angle JGF, I'm really just restarting what I wrote over there, is congruent angle JGK. Part B is angle JGK is congruent angle KGH. As soon as I can get away from saying those angles over and over, the better. I'm getting myself all tongue-tied. Part C is that the measure of angle JGF equals 6x plus 7. And part D would be that the measure of angle KGH equals, 8x minus 5. All of that we're allowed to call our given. Some of it is in the diagram, and some of it was in the description. Okay, so here's what we're going to write as our next line. Step number 2. The measure of angle JGF equals the measure of angle JGK. And because I'm going to use the same justification, I'm going to basically give myself a line 2 to this second step of my proof. And I'm going to write, well, also the measure of angle JGK equals the measure of angle KGH. So I've really just converted my first 2 lines of my given. I've converted those from congruent to equals. That's going to allow me to actually use my properties of equality. So our justification, as we discussed, that's going to be our definition, abbreviated DEF often, of, and we can write out the word congruence, but we also have a symbol. Might as well use the symbol, less writing for us to do overall. So there's that definition of congruence being used to convert between our congruence into our equations. All right, now that we've done this, properties of equality are on the table. And I'm going to take those 2 lines that we just wrote in the second step, and I'm going to cut out that middleman, cut out the measure of angle JGK to say the measure of angle JGF equals the measure of angle KGH. What is that again? That's our good old transitive property. Okay, we're almost into purely algebraic territory. Remember that we have these lines. I'm going to switch to blue here for a second. We have these lines. The measure of angle JGF is 6x plus 7. The measure of angle KGH is 8x minus 5. So here's where I'm going to take my expressions for those angle measures and plug them in or substitute them. And again, sort of saying like what we're doing is supposed to be a bit of a clue, right? Step 4, we just used our substitution property of equality. All right, now we're into algebra only territory. So we're going to solve this equation. I'm going to kind of jump through this quickly. So I'm going to perhaps, what do I want to do? Subtract 2x from, or subtract 6x from both sides maybe. So I'm going to write the result. If we subtract 6x from both sides, we get 7 equals 2x minus 5. That would be our subtraction. Notice the difference there between the substitution property, subtraction property of equality. Next, I might add 5 to both sides to get 12 on the left, 2x remaining on the right. So we have just added to both sides, use the addition property of equality. Okay, and we're almost there. Step 7, we would divide both sides by 2 to get 6 equals x. We divided, so that's our division property of equality. And lastly, same as before, since we have the same number for x, but it's swapped, it's reversed from what we want, we would say x actually equals 6. We know that through our symmetric property of equality. I added an extra m for no good reason. Okay. Ooh, that's our more complicated proof there. A whole 8 lines. Oh my goodness. Okay. We're going to end on this note. Oop, just kidding. And on this note, here we go. Reminders. Angle measures are numbers. Angle measures are numbers. Numbers can be equal to each other. However, the angles themselves are figures. They are geometric objects also. And geometric objects or figures, they can only be congruent. Angles cannot be equal to other angles, but their measures can. So this is why we used a line of our proof previously to state that whatever our angle was, now I don't remember, let's say angle A was congruent to angle B. We've got to use that definition of congruence to say, well, now let's say the measure of angle A equals the measure of angle B. Then we can use our properties of equality. Now, the same thing goes for segment lengths versus segments. So segment measures or lengths, those are numbers. We can say they're equal, but the segments themselves are figures, and they can only be congruent. Okay, so good reminder there. We'll see that in practice as well. But for now, I will say goodbye.